It's really an honor and a privilege to be spokesperson. It's going to be a very exciting moment. I'm very proud of what we, and we are many, have achieved in CMS. CMS is a technological marvel which has pushed many boundaries. And the moment of starting to extract the science is a pivotal moment and a very exciting moment. And we're looking forward to it, and a special moment. The detector is ready. In fact, we ran the detector in August of this year for a whole month round the clock, and we checked all the parts of the detectors. We recorded something like 500 million cosmic ray muons, and from there we can deduce that the detector is performing as we expect it to perform. And we also, the weekend of the 7th or 8th of November, took about 1,000 splash events. So these are beams which were sent around to CMS, and they were stopped in a collimator about 150 meters upstream of the experiment, and they lead to a large flux of particles which go through the experiment, and from there we can actually also check that the experiment is functioning well. So the results from these exercises are very encouraging, and this augurs very well for the future. In fact, we made the best possible use of the shutdown. Straight after the incident, we ran the experiment for about 6 weeks around the clock. And this was to check that the detector can actually run for a sustained period, and also to check our computing offline and analysis chains as well. And in fact, we recorded a very large number, about 300 million cosmic ray muons. And about 10 years ago, we had written down what the performance we expected from the detector. So this would include things like the efficiencies of detectors, the resolutions of the detectors in time, in space, and in energy, and aligning the detector and calibrating the detector, and so on. So these muons were used, in fact, to extract the performance of the detector, and the results were very encouraging, in fact. And also the analysis chains and the computing chains, the offline chains, worked well. The other things we did was also go through the first maintenance period, because after long runs we have a maintenance period, so this will be a thing that repeats itself. So this was our first maintenance period. We also installed the last major sub-detector, which was not installed, so we installed that, and that is also working very well. And finally, we refurbished some of the equipment in view of the long runs that we're going to be having in the future. So it was pretty usefully used. In fact, what we will do is when we get the first collisions, it'll be check the detector, not with cosmic rays now, but with collision data. So that's the first thing we will do. Now, the hope is that we'll go up to, so we'll take data at a 7 TeV center of mass, and something like of the order of 50 inverse picobarns will be very useful. The standard model makes predictions of known physics, and these are precise predictions of what is expected at the LHC energies. And these things include things like the characteristics and the rates of production of particles like the upsilon, the W and the Z, the top, and, for example, jet production. So we would expect to find in our data measurements which are in accord with the standard model. And this is a first step, a necessary step, before we could look for new physics. We have to be able to see the known physics, which is precisely predicted at the right rates and with the right characteristics. Now then, if we see something new, and we've done this work, then we could be in a position to claim new physics as such. So that's the first sort of thing. So in a sense, we will be physics commissioning the detector using known processes. Now, of course, at the same time, we'll be looking for new physics. And the hope is that we will push up in energy to something like 10 TeV and take a large data set at that energy. And there we'll be exploring new territory, both at starting at 7 TeV and going to 10 TeV, exploring territory beyond what is explored at, say, Fermilab. And hopefully we shall be finding new things. That will be very exciting. In fact, the experiment is a general purpose experiment. The muon is just because we concentrated right at the beginning of the design phase on muons, because they're rather difficult objects to trigger upon at hadron colliders. For the detection of muons, you need to figure out what sort of magnetic field configuration you want. And in CMS, we chose the high field solenoid. And the rest of the design then follows from that choice. And that's why the muon is quite important, in fact, although all the other particles like the photons, the electrons are just as important, because the Higgs boson, for example, can go into 2 photons, can go into ZZ, which goes into 4 muons, or 4 electrons, and things like that. So it was in the initial design phase that where the word muon comes in. The first thing, it will be very exciting, and it will be a pivotal moment, because it will mark the phase where construction has ended and we're starting the extraction of science. And so there will be lots of people in the control room making sure everything is going to work. So we'll be starting to take first data, and it will be something which is perhaps marking the second part or second half of this incredible journey to discover the secrets of nature.